It's my pleasure to introduce Paige Finley for her topic on insights into the activation of SOD. I told her I wasn't going to say the entire title. You can read it on the board. Paige.
Good morning, everybody. My name is Paige Finley, and today I'll be sharing with you the insights into the activation of the copper zinc superoxide dismutase by means of the copper chaperone CCS. By the end of this presentation, I'm hoping that you guys will be able to make sense of this jumbled mess of scientific terms that is throughout you. Okay, to begin, we all know that we use oxygen on a daily basis to perform basically all tasks of life. Oxygen is a vital component to life here on Earth. However, what most people don't know is that oxygen can be very damaging to our bodies if it is presented in excess amounts. Here we can see in this picture, in the production of energy in our cells, oxygen can gain an extra electron, becoming what is known as a superoxide radical. Superoxide can attack various parts in the cell, shown here, and cause damage that can eventually lead to cell death. Superoxide damage and oxidative damage in general can be thought of as a penny corroding. Just as a penny over time, after it's been left in your pocket, when it is exposed to oxygen in the atmosphere, becomes corroded and tarnished, that's what's happening inside of our bodies when superoxide and excess oxygen is present. Superoxide can break down automatically into hydrogen peroxide and oxygen, which our body can deal with. However, this reaction takes place too slow within our cells, so various mechanisms have developed within our bodies to help speed up this reaction. Here we can see that SOD, superoxide dismutase, is responsible for the breakdown of superoxide. In order for SOD to function, it needs to have copper inserted into it, which is where CCS comes into play. CCS binds to the SOD1 complex and inserts copper. CCS has cysteine residues, shown here in the yellow, that are thought to be essential and highly associated with SOD1 activity. Here we can see an example of this. These are growth tests done to show if SOD activity is present. Where we see the white dots here and everywhere else, that means that there is cell growth. When there's cell growth, that means that there's SOD1 activity. We can see that when mutations are made to the CCS protein, that cell growth is greatly reduced, shown here in the 231, meaning that the cysteine amino acid 231 is essential for cell growth. Just below, we can see that when copper is inserted, almost all cell growth is completely rescued, meaning that copper is playing a huge component in this SOD1 complex. Here, though, we can see that even if copper is added, if CCS is missing from the cells, there's no growth at all. Here's just another representation of what I just explained. We can see that when there's mutations made to the CCS, that there's very low SOD1 activity. Over here, we can see that the insertion of copper greatly increases the SOD1 activity in the cells. So far, we have concluded that the addition of copper to cells increases SOD1 activity. We've also found that increasing SOD1 in general is going to increase cell growth and SOD1 activity in the CCS mutant cells. My question is, then, shouldn't more CCS, even if it is mutated, increase cell activity? So far in my experiments, I am going to overexpress CCS, meaning make it present in higher amounts, to see if maybe overexpressing the CCS is going to increase the likelihood that copper is inserted into SOD so that it can become a fully functioning protein and rescue cell growth. Thank you for listening to my presentation.